Warhill chemistry students. I just finished getting some exercise, and I'm going to go in and learn some more about gas laws. Come on in. Let's go.
All right, so good morning. This is Mr. PVT man, or actually it's Mr. PV/T man. So in our last lesson, we learned that temperature and volume impact gas pressure. We also learned to convert Celsius to kelvins using kelvins equals 273 plus degrees Celsius. We made up a word. We made up the word kelvinate. So always kelvinate temperature. Now, don't use this word with your chemistry college professor because he's going to look at you funny, but we're going to use the word kelvinate. So, our objectives for today are to use the following equations to solve gas law problems. So there's all these 1s and 2 subscripts. All that means is that 1 means before and 2 means after. So what we have is P1 V1, pressure 1, volume 1, equals P2 V2. And we have V1 over T1 equals V2 over T2. And we have P1 over T1 equals P2 over T2. And we have a new cheer today. 2, 4, 6, 8. Don't forget to kelvinate. And remember, we do that by adding 273 to degrees Celsius. And then we're going to take these 3 gas laws and we're going to combine them into the combined gas law. So we're going to do one gas law at a time. We're going to start with P1 V1 equals P2 V2. We learned that decreasing volume at constant temperature increases collisions per area, thus increasing pressure. So this is P1 V1, this is P2 V2, and we see that we have an inverse relationship. So here's our first problem. A balloon contains 11 liters of helium gas at 101.3 kPa at sea level. What is the balloon's volume in Denver at 85.3 kPa at the same temperature? So Denver's at a higher altitude, so the pressure is lower. So the most difficult part of this for students is picking apart the beginning conditions versus the ending conditions. So yellow shows our beginning conditions and green shows our ending conditions. So I've identified my variables. So I plug this in to P1 V1 equals P2 V2, and I have 101.3 times 11 is equal to 85.3 times V2. Okay, now I've got to isolate V2. I'll do that by dividing both sides through by 85.3. And we end up that V2 is equal to 13.06, which rounds to 13 liters with sig figs. So, key thing here is identifying your beginning and your end. All right, you try this one. A piston compresses the air in an 0.52 liter cylinder, that's a piston, to 0.12 liters. So that's going to make it smaller. What is the final pressure if the original pressure was 760 millimeters of mercury? I've got the answer there for you, so pause the video to solve the problem, and then when you're ready, restart. Okay, so I highlighted the beginning things in yellow and the ending things in green and came up with the equation shown. Then I isolated P2 and I found that P2 is equal to 3,293, which I rounded to 3,300 millimeters of mercury. We're on to the second type of problem. V1 over T1 equals V2 over T2. So increasing temperature at a constant pressure causes the volume in a flexible container, such as a balloon or a cylinder with a piston, to increase, and we have a nice direct relationship. Now, we've got temperature in there, so 2, 4, 6, 8, don't forget to kelvinate. There's your equation. So here's our first example. Mr. PVT buys an 8-liter helium balloon for your friend's birthday. The temperature is 20 degrees Celsius, and the pressure remains constant at 101.1 kPa. How large will the balloon be after it sits in Mr. PVT's car at 60 degrees Celsius? So Serious note here. This is why you don't leave pets in cars, because when the sun is shining on a car, the temperature increases, and 60 degrees C is pretty darn hot. Okay, we're going to identify our beginning variables, 8 liters and 20 degrees Celsius, and our ending variables, we don't know volume, but our temperature is 60 degrees Celsius. 2, 4, 6, 8. Don't forget to Kelvinate. All right, there we've got 293, 333. We put them into our equation, and we're ready to solve. Now, the way to solve these type of ratio problems is what I call loop and circle. So I have an oval around the thing we loop and a square around what we're going to solve in the bottom. Actually, it's loop and square. So we multiply the things in the oval and we divide through by the things in the square. And this will work no matter where your unknown is. So calculator says 9.092 liters. When we round, we have 9.1 liters with significant figures. Now it's your turn. You have a 4.2 liter balloon at 45 degrees Celsius. What will be the balloon's volume at 15 degrees Celsius and the same pressure? I've got the answer for you there. Pause the video to solve the problem. All right, here's my answer. So I have underlined the things in yellow that are beginning, and the things in green are at the end. I remembered to Kelvinate, so I plugged everything into my equations. Then I cross-multiplied and divided, and I ended up with my final answer of 3.8 liters. We're on to our third type of calculation. As we increase the temperature, the particles move faster and faster and faster, so they bump into the particle wall or container walls faster and faster with more force and more frequency. So we have a direct relationship. And once again, 2, 4, 6, 8. Don't forget to Kelvinate. All right, here's a problem for you. Mrs. PVT checks her car's tire pressure in the summer. It is 2.3 atmospheres at 38 degrees Celsius. What will be the tire pressure in winter at minus 10 degrees Celsius? So yellow is our beginning conditions. Green is our final conditions. We're ready to plug them into the equation. Uh-oh, 2, 4, 6, 8. Don't forget to Kelvinate. So we changed our Celsius to kelvins. Now we're ready to plug in. So here's our equation, and we're going to cross multiply and divide. So everything in the oval divided by the stuff in the square. We get 1.945 atmospheres on our calculator. We round to 2 significant figures. Okay, now it's your turn. The pressure in a cylinder of gas is 760 millimeters of mercury at exactly 0 degrees Celsius. What is the pressure of the gas at 500 degrees Celsius? I have the answer, so you can check yourself. Pause to solve the problem and restart when you're ready to check. All right, so I've put my beginning conditions in yellow, my final conditions in green. I Kelvinated my temperatures before I put them into my equation. Then I rearranged and solved for P, and P is 2152. That's my P, which rounds to 2150 millimeters of mercury. Now, let's change all 3 variables. So we've done an example of this equation, an example of this equation, and an example of this equation. And now we're going to put it all together into the combined gas law. A balloon contains 10 liters of nitrogen at 100 kPa and 40 degrees Celsius. The balloon is placed in a chamber where the temperature is 10 degrees Celsius and the pressure is 10 kPa. What is the balloon's new volume? So, my before conditions, I identify those in yellow. I identify my after conditions in green. So now I'm ready to put all of it into an equation. 2, 4, 6, 8. Don't forget to kelvinate. So before I got started, I went ahead and I kelvinated my temperatures. Now I can put it into my equation. All right, so we've got this down here, which this looks kind of messy. So let me show you one way to handle this. So I combine everything in the red circle into one term and everything into the blue oval into one term. So then I have 3.195, that's what this is, equals 0.03534 times V2. Now that's easier for me to see how I'm going to solve it. So now I take 3.195, I divide it by the 0.03543, and I get 90.41 liters. But I need to do my significant figures, and that would be 90 point liters with sig figs. It's your turn. A weather balloon has a volume of 42.0 liters at 1 atmospheres and 20 degrees C. As the balloon rises to 1,500 meters, that's about 45,000 feet, the atmospheric pressure drops to 0.250 atmospheres and the temperature drops to minus 24 degrees Celsius. Gets chilly up there. What is the balloon's new volume in liters? I've given you the answer. You know the drill. You're going to pause to solve the problem, and then you're going to check and restart to see your answer. Okay, everything in yellow is the beginning conditions. I kelvinated what I needed to kelvinate. Then I put everything into my equation here. I consolidated everything on the left to 0.1443. I took 0.250 to divided it by 249 to get 0.00104, and then I solved for V2 and did significant figures. There's my answer right there. So you learned to use 4 gas law equations today. Here's the combined gas law. Here are the 3 basic gas laws. And we remembered that we are always going to kelvinate temperature. Coming soon! So next up will be the ideal gas law, PV equals nRT. Meanwhile, 2, 4, 6, 8, don't forget to kelvinate. 2, 4, 6, 8, Warhill students are really great. All right, guys, till next time, go out and get some exercise.